Good morning, everyone. This is Unit 8. This is 8B. And we're going to look through today. We're going to essentially build up to this model here. They call these things sinusoidal models. This is a rarely used word here. We're going to do this by looking at the unit circle, and we're going to develop today for 8B the sine graph, the cosine graph, the tan graph, and see where it comes from. Okay, there's a little investigation which comes straight after this. It's investigation 2, it's called here, and I've just stolen this thing here, and I've just put it in here. Now, this is the unit circle. The unit circle is what allows us to go beyond 90 degrees for trigonometry. You might have thought that it's kind of odd that in trigonometry we get our sine ratio, our cosine ratio, our tan ratio, and obviously you know that all comes from So I don't know, for example, you know that tan of theta, tan of the angle in the corner, is equal to the opposite length divided by the adjacent length, for example. And you've got your three formulas coming from each of these formula triangles. Okay, so it's a bit odd that we're allowing on a sine graph, because you probably already know the sine graph kind of looks like this, and it goes beyond 90 degrees. But of course, as I'm talking sine, I'm talking the tan graph as well. So tan graph is going something like this. You probably know that these things repeat. The reason why it goes beyond 90 degrees is because of this thing here. Right, so it's kind of odd that, for example, you would have tan of 90 degrees, because how could this be 90 degrees? That doesn't even create a triangle, a right angle triangle anymore. You can't have two right angles in a right angle triangle. And as soon as you go beyond 90, what on earth does that mean? So that's essentially what we're going to have a look at. Okay, let's just get rid of some of this here. Okay, so this all springs from a definition, and starting obviously with this thing called the unit circle. So without further ado, this is your 0 degrees or 0 radians. And here we define this, so we go anti-clockwise here, we define this as 90 degrees. And this we define as 180 degrees, and this is 270 degrees, and this is 360 degrees. And then you can keep going. So, for example, this is also 450 degrees. We add 90 degrees on. Likewise, if we went backwards, we could also call this minus 90 degrees. When you go around twice, you get 720 degrees, and this is also minus 360 degrees. We went backwards once. Okay, so those are the positions around our xy axes here for the unit circle. It's called the unit circle because you have a 1 here. The radius is 1, and you can see here you've got 1 on all of the axes here as well. Let's just get rid of some of that as well. And let's just do this in radians as well. So you have 0 radians. Normally you don't put anything on the end of that. Some people say rad. Sometimes you see a little C above, in fact, like just there, no rad. But normally people don't write anything. If there's no units, you can assume that it's radians. We've got 0 radians there. You've got pi radians is 180. You've got 2 pi is 360. So that makes this pi over 2 is 90 degrees. And so we've got 0, half, 1 lot of pi. So 1.5 lots of pi is going to give us 3 pi over 2 radians there as well. Those are ones worth remembering. And it's worth remembering, for example, that pi over 4 is equal to 45 degrees, half of 90. Pi over 3 is going to give you 180 divided by 3 is 60 degrees. And pi over 6, these ones turn up a lot. Pi over 6 is 30 degrees. Those are common radian measures that we should recognize. Okay, well, we still haven't come up with our sine graph or our cosine graph, so let's just look a little further into this unit circle. Just to recap, we start with 0 here. We go anti-clockwise. We count round to 90 degrees and so on. And we can go clockwise if we want to, but then we start going back in the negative theta, if you like. Okay, so how to get out the graphs? Well, if you have a look at this little triangle here, we know, let's start with sine. Okay, so sine of theta, we know from SOH, we know sine of theta is equal to the opposite divided by the hypotenuse. Well, the opposite in this triangle is equal to y, and the hypotenuse in this triangle is equal to 1. Okay, so sine of theta is just equal to 1. You divide y by 1, you just get y. In other words, the height as you drag this point round from side to side, the height represents sine of theta. So for example, at 0 degrees, that triangle is going to have no height. And you'll have a point which is here. So sine of 0 degrees is equal to 0. Y will be equal to 0 there. And at 90 degrees, again, you kind of have no triangle here again. The triangle becomes flat. You'll have a height of 1. So sine of 90 degrees will equal to 1. Okay, so we can put in sine of, should be 0. Sine of 0 is equal to 0. Let's do it in degrees just at the moment. Keeps it easy. Sine of 90 degrees is equal to 1. So that's just the height at this point here once we drag this point around. Now, if we drag this point around to the other side, we're going to get finally to this point here. And this point has a height of 1. So sine of, when we're pointing over to this side, a sine of 180 degrees is equal to, so that's a height of, I don't know if I said 1 there or 0, that's a height of 0. Height of 0. And sine of 270 degrees down here has a height of minus 1. And then when we get back to 360, we've got a height. Remember the height, the sine of theta. Height is y. So sine of 360 or sine of 2 pi is equal to 0 again. We've got a height of 0. Now we can start plotting those things. And we can plot at 0 degrees. So let's go up to 360 here. 180. Split that. That's 90 and 270. And let's go 1 here, minus 1 here. And so this is our axis for theta. And this is we're plotting sine of theta, which happens to be our y over here. So if we plot these things, so I'm going to plot these points here now, you get sine of 0 is 0, sine of 90 is 1, sine of 180 is 0, sine of 270 is down here at minus 1, and sine of 360 is back at 0. So there we go. We can put in our graph now. We can get out other points if we want to, but there's our graph in this case. I'm going to show you that again in a second. So if that's gone a bit fast, I will show you again. Just to kind of recap a little bit on this, again, we're starting at 0 degrees there, we're going around to 90 and so on. So we go round in this way. And that translates to our theta on a kind of XY graph, if you like, over to the side. Yeah, okay, and sine is trapped between minus 1 and 1. And this allows us, so say for example, this is 60 degrees. Well, this allows us, here we go, I'm going to just do a triangle over to the side here. I want to get this triangle over to the side. This triangle is seen to have an angle of not 60 degrees, so same height, distance across. This one's seen to have an angle of 90 plus the 30 there. Okay, it's 90 minus 60. So in fact, the sine of 60 degrees will give you the same answer as sine of 120 degrees. This is the triangle which represents 120 degrees in the corner. It's kind of a bit nonsense because the angle is not in the corner, but we're taking it from the definition of the unit circle. We're allowing this triangle to exist. And we're still applying the same opposite over hypotenuse rule. Okay, now from this, you can also find the cosine rule. So not the cosine rule, the cosine ratio. You can use this, and we'll find the cosine graph. So cos in this case of theta, we know that cos is equal to, comes from the K triangle, formula triangle. So we've got cos of theta is the adjacent over the hypotenuse. Now the adjacent in our triangle is x, it's the length which is next to the angle, not opposite, obviously. So that's equal to x, and the hypotenuse is still equal to 1, so cos of theta is equal to x. So as you go round here, so if you start off with triangle, if you like, which is sort of squash triangle with theta is equal to 0 degrees, you see that your x length is 1. We have a distance across of 1 here. So the Cos graph plots distance across for any theta around the outside. So cos of 0 is equal to 1. Cos of 90 degrees is equal to 0, because at this point, at 90 degrees, we can see that we have a distance across of 0. We have a height of 1, but a distance across of 0. And cos of 180 degrees is equal to, there's 180 degrees over to here, the distance across is minus 1. Cos is distance across, cos is x. Okay, and you can continue that, and you'll see, you'll get your Cos graph as well, which most of you are familiar with. It starts at 1. Let's just space it out correctly. There's your 360, there's your 180, and so Cos is going to come out like this. It's going to come out between 1 and minus 1. You need to be able to draw these things, sketch these things quickly, so make sure that you're doing that throughout the exercises as well. Okay, right, I'll show you that again in a second. There's another thing to note here, that your identities come from this too. So for example, tan of theta we know is the opposite over the adjacent. The opposite in our triangle is y. The adjacent is x, that's this distance across here. Now we know that sine of theta was equal to y and cos of theta was equal to x. So there we go, we've got this identity here, tan of theta is equal to sine of theta over cos of theta. We've used that already in unit 10, but that's one of our identities. Also, if we use trigonometry inside this little triangle that we've got here, sorry, not trigonometry, Pythagoras, then you can see that you get x squared plus y squared is equal to 1. Well, x we know, again, is equal to x, we got it over here to this side, x is not equal to sine, it's equal to cos of theta. Now that's cos of theta squared plus y we know was sine of theta, put a squared there, and that's equal to 1. And that's always true, in fact, and because it's always true, this is an identity. It's true for all values of theta. And the same with this one at the top, actually. That's also an identity. It's true for all values of theta. It's not an equation which we need to solve. We normally write this one, though, like this: sine squared theta plus cos squared theta is equal to or is identical to 1. So this is a formula which we can use at any point. This is an identity which we could use to help us solve any equations if we needed to. Okay, just a little bit more. I'll just show you on here on My Maths. There's some good little lessons on this one. If you want to go to My Maths, the password is whiz, so the same as last year. If you used it in year 11 or year 10. The login is whiz, W-I-S, and the password is decimal. That's to get to My Maths. And if you go to the library function, and if you go to, I went to core 2 and I went to trigonometry, you can see there's a lesson on the sine graph and the cosine graph and the tangent graph as well. So for the sine graph, you can see they've got the unit circle set up here, and you can click through at the bottom to do your next. And it says, well, what's sine of this angle here? Sine is the opposite over your hypotenuse, or the opposite has a height of 0.87, and we have a length of 1, so it gives us 0.87 in that case. Right. So from this, what's quite nice is this thing here. So if you take the magenta line, or the pink line, if you like, and you lift it up a little bit, it's plotting on the graph to the side the height, and the height, remember, represents sine. We keep plotting this, and it will build up our graph. We're getting to 90 degrees now. 90 degrees, we have sine of theta is equal to 1. Sorry, sine of 90 degrees is equal to 1. Okay, and this is ending up plotting our graph. This is what our sine graph looks like. So that's kind of nice. You can have a look through that if you want to. They also do the cosine graph there. In order to do the cosine graph, they switch this around because they're plotting the distance across. So they've just moved it around. So again, same, we've started with that pink line facing to 0. We've just moved it around a bit. And again, the distance across is 1, although that's now plotted as a height on our graph. So there we go, there's our Cos graph, which is coming out for this one. Now, the tan graph is less obvious. I'm going to just show you on Desmos. So we go to Desmos here. This is the sine graph. What's quite nice with Desmos, if you type in y equals sine of x, if you then go to, now it will always give you things in radians, not in degrees. And if you type in pi in the step, then it will sort out the axes nicely for you as well. So you've got pi over 2, pi there is 180 degrees. And this is the default, basically. You can probably change it into radians. Yeah, you can change it into degrees here, but then it will look completely flat because then you'll need to change your axes from, let's have a look, go up to 360 degrees. There we go. And so there's our sine graph. Now we don't want it in terms of pi. I need to change this again. And my step, I might want to go up in, I might want to go up in 90 degrees. And there you go, you can see that. Let's just sort the y-axis there. So let's go from -2 to 2. So there we go, there's our sine graph. Okay, that's sine in terms of degrees. Your calculator will give you a default of radians in general. And remember that you'll need to change your mode between radians and degrees depending on what you're working in, both in the calculator mode and on the scratchpad mode as well. So you need to be able to navigate that quickly in an exam situation. All right, let's have a look at cos of x here. So there's cos of x. And tan is less obvious. Tan is the division of the two, remember. So tan is sine of x divided by cos of x. That's tan. It's the same thing as us saying tan of x there as well. So tan of x is kind of interesting because you can see you have an asymptote at 90 degrees. Let's just take this back. And there's no asymptotes for sine and cosine. What else to say on this one? Yeah, it's interesting, I suppose, to note that, for example, for sine repeats every 360, obviously, because of the way that we constructed it, and so does cosine. But when it comes to tan of theta, you should be able to sketch all of these graphs quickly. You can see that this one repeats every 180 degrees. And you can see as well, it's got, there we go, this one here, and x is equal to 90 degrees. So you can see there are asymptotes at -90 and at 90, and we have this repetition here as well. What else to say? I think perhaps should just say a couple of other things before we do a separate video on the questions which are given. So let's just steal this for a moment. It's worth noting that on your calculator will only give you values for inverse sine. So say, for example, you say, well, I want to know what inverse sine of 0.5 is. Your calculator will give you this answer. It will not give you this answer over here, but you will be required to work those ones out as well. Or, for example, this one over here, it will have a height. These are all x values, which give you a height of 0.5. So if you're solving sine of x equals 0.5, and you're allowed to go beyond 90 degrees, you'll have to use your graphs on your calculator to find those other values. There's other ways of doing this. The cast diagram, there's these diagrams too, but we won't go into that too much. On your calculator, your calculator will only give you answers. If you go backwards, you use backwards sign. Okay, so inverse sine, it will only give you answers between -90 and 90. It will not give you further answers. So, for example, if you put in sine to the -1 of, let's say, -0.8, it will give you some value around here, depending on whether you're in degrees or radians, of course, from your calculator. It will not give you this value here. It won't give you that. You'll have to figure that one out yourself. Let's just get rid of all of this. So inverse sine gives you values between -90 and 90. And inverse cosine will give you answers between where we have a one-to-one function between 0 and 180. So for example, if you do cosine to the -1, inverse cosine of, say, for example, -1/2, it will give you a value around here. You will not get the other one here. Though you might be able to see there's some symmetries happening in the graph there. I won't go into that now. Likewise with tan, your tan graph looks something like this again. A bit messy, but it looks something like this. So for your tan graph, if you do inverse tan of something or other, and you can see you can go beyond -1 now. So if you do inverse tan of, let's say, -2, it will give you this answer here. It won't go beyond and give you the next one beyond the first asymptote. It will not give you this answer here. So you'll have to work that out yourself, and that's pretty easy, to be honest, because you're just 180 degrees further on. Guys, I think I've spoken enough about this one just at the moment. Thank you for listening in. You might want to watch that one again. That's quite a lot to take in at one point.